Alright everybody, in this video let's try to implement the remove functionality on a singly linked list. So what exactly this remove operation does on a singly linked list is basically it is used for removing the node at a given position that is requested by the user. To give a specific definition as part of this remove implementation, what exactly we will do is we will basically take the index from the user and we will basically go to this index and whatever the node that we have at that particular index, and we will simply try to remove that node, and in the end we will simply return that node back to the user as a output. Okay, so that is the ultimate functionality of a remove operation on a singly linked list. Here obviously we are taking the index from the user, right? So obviously there would be two cases. The first case is the valid index and the second case is invalid index. Here if you observe the singly linked list that we have, right, we know the valid values of index on a singly linked list will basically start from 0 and will end at length of the singly linked list minus 1. So for the remove operation, the valid range of the indexes will be from 0 till the length of the linked list minus 1. That means in the singly linked list that we have here, right, the indexes will be at 0, 1, 2, 3, 4 and 5. If user passes any of these indexes, we will be able to delete that node and we will be able to return the value. And one thing that you have to make sure here is whatever the head node and tail node and whatever the length that we are maintaining on the singly linked list, right, we have to make sure that those values are still consistent even after deleting the node from the singly linked list. That is something that that we have to remember. Now let's just try to understand whatever the different cases that can come when we are trying to implement the remove operation on a singly linked list. The very first scenario is basically, since we are taking the index from the user, right, first check would be to check if the index that user is passing is invalid. So that is the first check. When we will say the index is invalid, if the index is less than 0 or if the index that is given by the user is greater than or equal to the length of the linked list. If user passes the index that falls into this range, we will simply return null or none based on our programming language that we are using for implementation. If we are using Java or JavaScript, we will simply return null. If we are using Python based implementation, we will return none. Okay, so that is the first scenario. And the second scenario is obviously a valid index that is given by the user. So in the valid index also, what exactly we will do is we will try to reuse some of the functionalities that we have already implemented. So if you remember the previous implementations that we have done it, right, in those cases, basically when we spoke about those functionalities, specifically when we spoke about the pop functionality and the shift functionality, pop functionality is basically used for deleting the very last node we have in the singly linked list, and the shift operation is basically used for deleting the very first node we have on the singly linked list. So whenever the user is passing the valid index, we can reuse this push and pop shift functionalities. So how will we make use of that is, inside the valid index scenario, as part of the first check, what we will do is, if the index that is given by the user is 0, we will check. If it is 0, right, what exactly we need to do? We need to delete the head node, right? We have to delete this head node. That means whatever the next node that we have inside the singly linked list, that should become the new head of the singly linked list. That's why here this operation is nothing but the shift operation. So we will simply call the shift operation with whatever the index or 0 itself we can pass, because whatever the index that user is passing is 0. In the end, this shift function automatically returns the node that it is deleting, right? And we can return that node itself. Okay, so that is the first scenario. And the second scenario is basically if the index that is passed by the user is equal to the very last we have very last index we have on the singly linked list. That is, if the index is equal to the length of the singly linked list minus 1, and we are anyway maintaining the length in our singly linked list, right? And we will be able to get that length directly, and we will be able to compare it very easily as well. So if it is matching this case, that is nothing but we are trying to delete the very last node we have on the singly linked list. That operation is nothing but pop operation. So we will simply call the pop operation directly. Okay, and I forgot to mention, when we perform the shift operation also, we will not pass any index as an argument, right? Because shift operation itself will basically delete the very first node. So it automatically knows that it has to delete the current head node which is at index 0. So this is a small change. By mistakenly I have written index as a function argument. Okay, now the third scenario in the valid case is basically if the user passes any index from 1 till the last but 1th index. In that case, what we have to do is we have to make sure that we are deleting the node at the index that is given by the user. And now I will explain you what exactly is the algorithm that we follow. Now here, let's assume that the singly linked list that we are using for performing the remove operation contains, let's say, some 5 values or 5 nodes in it. And we have the head node and we have the tail node, and these will have some values like 1, 2, 3, 4, 5 or some other random values they will contain, right? And the indexes will be 0, 1, 2, 3, 4. Now we have already understood when the user passes the index 0 and when the user passes index 4, we have already handled those scenarios. Now our worry is if the user passes an index from 1 to 3, right? Now let's assume that in our implementation the index that is given by the user is 2. So we have to delete this node with the value 3 because it is at index 2. Now to delete this node, what we have to do, we have to make sure that whatever the next pointers that we are keeping track of in each and every node, we have to make sure that we are deleting that. So to do that, what exactly we will do is, first we will get the node that is at whatever the index that is given by the user minus 1th position. So in our case, the index that user has given is 2. So we will go ahead and get the node at the index 1th position because we are trying to get the node at index minus 1th position. Because index minus 1th node will contain the next or the reference of the node that is at the indexed position in the next variable of that particular node, right? So we have to make sure that that node we are updating it to the next of the node that is at indexed position. So what exactly we will do, we will get the node that is at index minus 1th position and we will update the next of that particular node with the next of the node available at indexed position. That means that this node's next will be having the value of or the reference of the node 4. In that way, this node is actually getting deleted. Okay, I hope you understood. What exactly we will do is, first we will go ahead and we will try to get the node that is at index minus 1th position, because in that node we have the reference of the node that is at indexed position. So what we will do, we will simply update that next variable or that next value with the next of the node that is at indexed position. So that is the third scenario where index is greater than 0 and less than length of the singly linked list minus 1. That means that the very last index that we have. So as part of the singly linked list implementation, let me define a function called remove. This basically will take the index at which we need to remove the node, right? So the possible values for the index are basically from 0 till the length of the linked list minus 1, because we have the valid nodes in that range. But still, whatever the index that user has passed could be still the invalid index. To eliminate such cases, write the base condition if this index is less than 0 or if the index is greater than or equal to length of the linked list. In this case, we will simply return null, indicating that we haven't deleted the node at the index that you have given because it is an invalid index. If this is not the case, then whatever the index that user has passed, that could be 0. If the index that is given by the user is 0, that means that we want to delete the head node itself. That means we are trying to perform the shift operation. So we will simply reuse the shift operation that is already being implemented. Okay, so we have successfully deleted the head node and we have made the next node as a new head of the singly linked list, and we have maintained the consistency. Otherwise, the other scenario could be whatever the index that I have passed could be same as the last index, that is the length of the linked list minus 1. In this case, we are trying to delete the very last node, that is tail node. That is nothing but pop operation. So I'll simply return this dot pop operation. I will reuse it. Okay. Apart from any other case, what we need to do, I need to go on to the node that is at index minus 1th position, and I also need to get the node that is at the index plus 1th position also. Now for the index minus 1th node, if I assign the next as to the node that is of index plus 1th position, we would have deleted the node that is at the index position. So for that, let me just define a variable called node. For this, let me just call the get function and get the node that is available at index minus 1th position. Okay, now the node that needs to be deleted is, that is node to be deleted is at index position, right? That is nothing but node dot next. Okay, now the nodes that is at index plus 1th position will be the next of the node that needs to be deleted. So let me just take const next nodes. Let me just read it as node to be deleted. Okay, E missed here. Node to be deleted dot next. Okay, so we have the node that is at index minus 1th position. Node to be deleted contains the node at index position. Next nodes contains the node that is at the index plus 1th position. So now all we have to do is, to this node variable dot next, we should assign the next nodes. So node dot next, we will simply make it as a next nodes. Okay, so we have basically deleted this node that is at the index position. Since we have to return this node, right? We basically set the next to null so that whenever the user tries to capture the return value and use it, he will not have the access to the remaining linked list. Even if you skip this part also, it's absolutely fine. That's not a mandatory thing. Since we are trying to remove one node from the linked list altogether, the length should get decremented by 1. So this dot length minus 1. In the end, we need to return the node that we have deleted. So that is inside the variable node to be deleted. Okay, this is how we basically perform the remove operation for all possible indexes given by the user. Now let's just try to call this remove operation and validate the result. So in the input linked list right now, we have 4 values like you can see on the screen here. Head node is being 10 and the tail node is being 10.134. Okay, so as part of here, let me call the remove operation. Let me just pass the index 0 in the beginning. Before remove we are traversing, and after remove also we are traversing, just to see the difference here. Okay, if I call the remove operation with index 0, that means we are trying to delete the value at 10, right? So the resulting linked list should contain only these 3 values. If I execute it, simply node singly linked list dot JS. If you see here, before remove operation, the traverse operation printed all the 4 nodes, and after remove operation, we've got only 3 nodes. Okay, if at all, if you want, you can just unblock this head and tail values and validate the results too, so that you will have a even clear understanding. Okay, after removing the head node is codingpal.r, because we deleted the node at index 0, the next node will become the new head node. Okay, similarly, if I pass the index as 3, that means the last index here is 3, so the tail node should be removed. So it will basically reuse the pop operation that we have added as part of the remove functionality. If I execute it, you should see before removing we've got all the 4 values. After removing we've got only 3 values. In that also, since the last value 10.134 is being deleted, right? So the tail node will be true. So that also we have got here, and the length of the linked list is 3 that you can see. Okay. Similarly, if I pass any index also, let's say if I pass 13, 13 is not a valid index because we have only 4 values. If I execute this remove operation, basically we should not see any difference in before remove and after remove, because it is an invalid index and the remove operation is not possible. Similarly, if I remove any node that is at index 1, so here the node at index 1 is codingpal.r. If we remove that, the resulting linked list will be 10 through 10.134. If I execute it, you see before remove and after remove, and we have removed the codingpal.r successfully, and the resulting linked list has a head of 10 and a tail of 10.134 and a length of 3. Okay, this is how basically we implement and evaluate the remove operation on a single linked list based on the index that user has given. So here, when will the best case scenario of the remove operation will actually occur? Whenever we are trying to remove the very first node on the singly linked list. That means we have certain number of nodes available on our singly linked list, and we are trying to perform the remove operation of a head node. That means that we are reusing the shift functionality, right? When the user passes the index 0, we are deleting the head node itself. Obviously, we know shift function will automatically take constant amount of time. So in the best case scenario, the time complexity of remove operation is order of 1, which will basically occur when we are trying to delete the head node of a singly linked list. Okay, when will the worst scenario of the time complexity will actually occur? Whenever we are trying to delete the very last node on a singly linked list. That is nothing but we reused pop operation, right? What exactly pop operation had to do? It has to go to last but 1th node, and it has to update the next of last but 1th node to null, right? That's why we have to run a loop for n number of times to reach the last but 1th node. As a result, in the worst case scenario where we are trying to delete the very last node we have on a singly linked list, the time complexity will be order of n, which is nothing but the time complexity of the pop operation. Okay, that is how time complexity and space complexity are calculated in terms of best case and in terms of worst case scenario. Now let's go ahead and let's just try to understand the space complexity of the algorithm that we are writing. Obviously, in the best case, we are reusing the shift operation where we are trying to delete the very first node on a single linked list. In that case also, we simply, we will not do anything. We will simply take one variable like current head, and we will simply update the head node to the next node by using that simple current node or some other temporary variable. As a result, in the best case scenario, the space complexity will be order of 1 only. Okay, so in the worst case scenario, yeah, we will run a loop for n-1 number of times to reach the last but 1th node, but we will go to that node with the help of a simple variable called current node. If you remember the pop operation, right, we have taken the help of a current node. Using that current node itself gets updated with the subsequent next nodes as we progress further onto the singly linked list, till we reach a point where we are at the node that is at index -1th position. As a result, even though we are running the loop for n number of times, we are reusing a simple single variable like current head or some other temporary variable. Okay, as a result, in the worst case scenario also, the space complexity will still remain order of 1 only in terms of performing the remove operation as well. Okay, so that is the time complexity and space complexity analysis of a remove operation on a singly linked list. Okay,